So in this chapter, chapter 5, we're going to start looking at RC and RL circuits. So RC is resistor capacitor, and RL is resistor inductor, and we had that previously mentioned in chapter 1 and 2 briefly. But RC and RL circuits are first order circuits, and they do some interesting things and allow us to have a greater toolbox of knowledge for our electrical design. So RC and RL circuits in general can be used for smoothing signals. They can be used for filtering out frequencies that are unwanted. They can be used for conceptual purposes as well and solving different types of equations. Or they can be used in conjunction with op amps to solve much more advanced op amp functions. And so both of these types of circuits are important in electrical engineering as they add more diversity to our ability to calculate out different circuits. So in this chapter, we're going to go through a few different types of RC and RL circuits. I'm going to introduce how we add capacitors together in series and parallel, how we add inductors together in series and parallel, how to solve the differential equations, the first order differential equations for these, and additionally what they can be used for and why they're an important circuit element to use in the future. So without ado, let's go into RC and RL circuits. So the first part of this, we're going to actually look at some op amps just to make sure that your knowledge on op amps is set, because there's going to be a lot of op amp applications using RC and RL circuits. So we're going to knock out some of these first. This is going to be a quick self-quiz that you can kind of go through. I'd encourage you to pause the video and try to work through these and see if you can solve them out. Each one of the numbers corresponds to a lettered circuit, and then in order to help you, I've put the gains underneath there so that you can kind of see the equation for gain. So most of these are asking for the V out based upon the gain function. So I'm going to let you pause that there, and in the next couple slides, I'm going to show you the solutions for these. So feel free to pause now. So here we're going to go through the answers for some of these op-amp circuits. So in number 1, if R1 equals 2 kiloohms and R2 equals 10 kiloohms, what is the gain of circuit A? So let's look at circuit A. Let's see what kind of op-amp circuit. Let's identify it correctly. That's the hardest part of these, identifying it. So I'm going to see that the signal Vin is going into the inverting input, and therefore I'm going to say this is an inverting amplifier. Therefore, I'm going to use the two resistors in the configuration for the inverting. So that's going to be 10 over 2, and then a negative because it's inverting. So it's going to be what? 10 divided by 2 equals negative 5. Gain equals negative 5. Bingo. So let's look at the number 2. If R1 equals 3 kiloohms and R2 equals 9 kiloohms, what is the output of circuit B for an input of 0.2 millivolts? So we're going to look at the gain again for this. What is the output? That's what that one's asking for, right? So let's identify this circuit. This circuit is a, what? We have a Vin going into the non-inverting section. So this is a non-inverting amplifier. And therefore, for a non-inverting amplifier, we've got 1 plus R2 over R1 as our gain. R2 is 9, divided by 3 is 3, gain of 4. So we're going to take the 0.2 millivolts and multiply that by 4. And that's going to bring us up to 0.8 millivolts as our V out. Cool. We're going to look at number 3 now. If the input to circuit C is 2 sine of 2 pi 60t, what is the output? So let's find circuit 3. What is that? C. We go down. We find circuit C. So that looks really complex coming in because it's giving us a trig function in there, getting us a wave. But we look at the circuit, it's just a buffer circuit. So the gain is 1. So the input equals the output. 2 sine 2 pi 60t. It's an easy. It was a trick question. So let's look at number 4 now. For circuit D, if VA equals 2 volts, VB equals 6 volts, and RA equals RB equals RF, what is V out? So let's go to circuit D. Let's look at what that is. I identify that one as a difference amplifier. And so next part of the circuit is RA equals RB equals RF. RF is going to cancel RA. So RF divided by RA is going to be 1. And then RF divided by RB is going to be 1. So we're left with VB minus VA. So VB equals 6 minus 2 equals 4 for our V out, 4 volts. Bingo. So now we finally have our number 5 here. For circuit E, if VA equals 2, VB equals 6, RA equals RB equals RF, what is V out? So it's similar to the other one, but a different circuit. So let's identify E. Let's go to that in the bottom corner. Looks like an adder circuit to me. We're going to add those together. So if we go down to the adder equation, RF and RA are going to cancel out. So it's going to be 1 over 1. So 1. So negative VA plus VB. Negative VA equals 2. And VB equals 6. And therefore, we're going to get minus 8 because they're going to add together for that circuit. So these aren't too bad. I think the hardest part is just correctly identifying them on this slide. So without ado, let's continue. So previously, we've had this slide, actually, this exact slide about resistors, capacitors, and inductors. I believe it's chapter 2 that you can go back and look at. And this gives you an overview in that of what these different types of resistors, capacitors, and inductors are. And I know some of you were wondering why I introduced them all at once. Well, it was either introduced them then or now, and we could use capacitors and inductors in different projects. So to me, it made sense to introduce them all previously. So just as a quick wrap up, for resistors, that's the one we've done the most amount of work with. We have different sizing of resistors. Resistors values can be determined by the color bands that are on them, and also by plugging them into a multimeter and checking the resistance, an ohm meter specifically. And then down in the bottom left hand, we have different wattages for resistors. So in general, the bigger, the wider the resistor is, the more watts it can take before it burns out. And if you guys want to see a burnt out resistor, I have a couple from previous projects that people have done. So they go completely char black usually, kind of cool to look at. But essentially, you size your resistor for the amount of wattage that goes through it. And you do that, remember, watts is power. Power equals current times voltage. And also you can solve V equals IR into that to be able to get two currents in a resistor or whatever different values you have available. Capacitors in the middle, we've got a whole bunch of different types of capacitors, electrolytic capacitors, ceramic capacitors. Electrolytic capacitors generally have a positive and a negative direction. Ceramic capacitors generally are non-directional, so it doesn't really matter. Resistors, to go back to that, are non-directional. It doesn't matter which order you put them in. So capacitors we've introduced previously. Please go back to the previous slide or look on YouTube or whatnot to be able to familiarize yourself with these. And finally, on the right, we have L, which stands for the symbol we use for inductors. Inductors are essentially coils of wire that wrap around some type of ferric material, a magnet or whatnot. So the ring one there is a toroidal coil. Sometimes they're cylindrical coils. They have a whole bunch of different types of inductors, but generally it's a piece of metal that's coiled around some type of conductive material. Sometimes it's open in the middle too, so depends on what the inductor's value is. So inductors generally, as a rule of thumb, and when we're trying to use RC and L circuits, if you're trying to do a smoothing circuit for some kind of filter or whatnot, we generally try to use capacitors and not inductors because capacitors are easier to produce in different values. Inductors, since there's a coil there, and the coils can be spread a little bit different, the inductors are a little bit more expensive, and they're also not always as reliable or as exact as capacitors. So in general, if using for filtering circuits, we stick with the capacitor-based version, although keep in mind inductors can be used just as fine. So what are these RC and RL circuits used for? So primarily, we're going to introduce these as in a signals and systems method. to be able to take noise, reduce noise out of circuits, and also to filter out for certain frequencies that we do want. So filter noise out of the circuit, filter a selected frequency, or maybe even clean up a signal so that we can do something with it later on, or do a different mathematical function on it. So in these slides, we're going to introduce essentially a basis of signals and systems, and how and why noise and filtering is important for them. So here we have three different biomedical signals: EEG, ECG, and EOG. EEG is electroencephalogram. That is a signal that essentially comes from your brain. It's a way, in layman's terms, it's reading brain waves. So you can see actually that signal is a very choppy signal. There's a lot of different noise inside of there, and all that choppiness that comes through, that's noise that is caused for a bunch of different reasons. Sometimes it's caused by external factors like a cell phone going off, or your 60 hertz power going through your house. But it also can be caused by essentially the signal reflecting off your skull. So when there's an impedance mismatch, we'll get to what impedance is in a little bit. But when there's a mismatch of material, you get something called reflections. You get absorption, and you get multiple reflections. So some of that noise is also due to reflections that happen within the brain as well, within the skull. So the next one, ECG, electrocardiogram. The electrocardiogram is another signal. This one looks a little bit cleaner. There's still a little bit noise in there, but you see those high peaks? That's essentially, if you want to go into the biomedical terms of it, you have something called your complexes, PQRS complex, and essentially it's just different parts of the heart polarizing or beating and depolarizing. So you get a positive when it beats, and then it has to essentially come back to negative, back to normal. So you get a rest stage where it dips down. So that peak, that large top peak that you see repeatedly there at pretty evenly spaced patterns, is actually the larger part of your heart beating. And then the dip down under zero is actually your heart essentially resetting so that it can beat again in a little bit. And then the little peaks up are actually the smaller parts of your heart beating, because your heart doesn't always beat at once. It's a pump, so different sections of it beat in order, and that's what essentially lets blood flow, just like a pump does. So again, that's the ECG. And then finally we have EOG, electrooculogram, if I remember right. And so EOGs are essentially measuring signal from your eye. And this is a way that you can do like eye motion tracking and some different eye readings. And you'll see there that it's a very stretched out signal. That doesn't mean that there's not noise in there. There's a whole bunch of tiny little bits of noise. But in general, to me, it looks like it's a little bit cleaner of a signal coming out. But there's also less pattern there as well, as compared to the ECG, which has a very distinct pattern, and the EEG, which has a very distinct high frequency pattern and a less distinct but still present low frequency pattern. So noise and filtering is important because all three of these have noise in them. And sometimes this is going to make it so that we can't do anything with it, or it's going to trip our sensor when we don't want it to be tripped. In general, we want to smooth this noise down. So in the bottom, in the red there, this is a smooth signal of an ECG. So you see that polarization, that top peak there, that's what it should look like. And then you have a peak down, and then you have a smaller peak up, which is kind of spread out, and then you go back to normal, and then you repeat it. And that's what the ECG pattern, the second one down, should look like. But you see there's a whole bunch of other little lines splintered out through there. That's because this ECG probably hasn't been filtered properly. The bottom one has been filtered much better because we get a much easier curve, a much smoother curve, and it's easier to see what we're looking for in there. So all that, if you go back to the middle one, all those tiny little up and downs are a high frequency signal that's added on top of the signal that you want. And the signal that you want is the one below. So let's just say we take op amp and we do a difference amplifier. We can take the ECG and we can subtract the noise. And if we take this middle ECG reading and subtract the noise, you're going to get the reading in the bottom at pink, which is essentially the cleaned up and filtered version. So there's other ways of doing filtering too. Again, sometimes even within the heart, you have other biosignals like muscles above there. Myocytes produce a lot of actually myocytes are really good at making an electrical electrical signal. which is why also that if you're wearing an EEG, which is a much harder signal, brainwaves are harder to get because it's again inside the skull, and muscles are really good amplifiers, natural bioamplifiers. But if you're wearing an EEG to measure your brain waves and you start twitching your muscles or moving your face muscles, that can really throw the EEG off because your facial muscles and your scalp muscles overpower the EEG signal because, again, muscle is a great amplifier, natural amplifier. So on this slide, we have a signal here at the top. This is actually, again, an ECG electrocardiogram. So this is essentially the signal coming from a heart. And so what we have here is, it looks a lot different than the pink one that we looked at in the previous slide. And that's because that there's a 60 hertz noise in the background from an AC power line. Because remember, the AC power oscillates at 60 hertz. It oscillates 60 times per second. And that's the predefined measure that we've picked and we've standardized in the US. If you go over to Europe, it's 50 hertz, so slightly different waves. So actually, a lot of the filters that you use for this kind of thing have to be tuned to your location to make sure that you have the correct filter for the correct location. So a lot of filtering electronics, and actually a lot of electronics in general, will not work if you pull them directly from Europe over to the US or back and forth. So anyway, in this picture at the top, you see there's this jagged up, down, up, down, up, down that's like high frequency compared to the lower frequency heartbeats that you can see the giant three peaks for. So if we go to the bottom here, you see again the blue, which has all the peaks, and this higher frequency 60 hertz noise. And again, 60 hertz means 60 beats per second. Your heart is not beating 60 beats per second. It's beating like 1 beat per second, maybe around there. Let's just use that as a guess right now. So all those little lines in between there are happening because the wall is essentially beating, if you want to think of it that way, so much faster than your heart. It's beating 60 times faster, so you're going to have 60 of these little tiny jagged lines in there. So in the bottom here, in blue, we have that natural signal from the top. In red, we have removed, either with a difference amplifier or a filter, the frequency that is the 60 hertz noise. So the big point from this is essentially frequencies can add and subtract. So you can remove some frequencies, especially if they're constant, like 60 hertz is a very constant frequency. We can remove that out of a set of data, and we're going to show you how to do that. But in the bottom right-hand corner, again, the blue is your input. If you remove 60 hertz from that, the 60 hertz signal from that blue signal, you get left with that red signal, which is a much, much cleaner version, and we can do better math with that, and we can actually look and analyze it much better from a physiological standpoint. So a doctor can see problems that are happening where if you give them the signal in the top left, it's much harder for your eye to identify what's happening there. This can be especially important in things like tachycardia. So here we have an ECG with an EMG overlaid. So this is a really kind of fun slide. I like this one a lot. So if you look on the left hand before like 2 seconds, you have a pretty clear actually beat of a heart. You see your QRS complex, PQRS complex. You have actually a pretty cleaned up signal there. But then it's around 3 seconds, all of a sudden you get noise, so much noise. And you're thinking, well, if I was measuring right before and now all of a sudden I get all this noise, where is that coming from? And it's actually, it's coming from muscle. So like I said previously, muscle is a really great amplifier. Your heart is a giant muscle and it amplifies. The reason that it's easily covered up is because by like a pectoral muscle or some muscle above, it's because essentially the heart muscle is deeper in your body. And it's a little harder. Some of that signal attenuation is lost due to surrounding tissue, especially bone in there, because again, you get impedance mismatch, you get mismatch of types of material, and that's going to suck up a lot more energy. So it's a little bit harder to read your heart when you have a pectoral muscle, which is right underneath your skin, and that's a muscle in general is a great amplifier. So if you had originally from time 0 to 2 here, that's essentially just your heart beating. But if you flex your pectoral muscle, essentially your heart's still beating underneath of that. The signal is still in there. But the pectoral muscle now is overlapping on top of that, and that's making a very noisy signal. So In this chapter, we're going to try to look at how to remove either the pectoral muscle or remove the heart to look at just the pectoral. And that way we can get a data set that maybe we can use in the future to remove a pectoral muscle because it has a different, essentially a different frequency. So filtering is important because if noise does not enter the signal, how do we get rid of it? Essentially, this is how we can pull signals apart. And so there's a really cool mathematical principle that you were introduced to actually in physics 2, and you were introduced again in differential equations, but we really want to hit it home with some hard examples now. And this is called the concept of Fourier analysis, or the Fourier concept. And essentially what that's saying is any signal, really complex signals or whatnot, like this one in blue on the left hand is a very complex signal. There's a lot of stuff going on in there. That complex signal can be represented and broken down into a sum of smaller signals that are all sine waves. So that blue signal, if we look, can be broken down into this signal on the right, which is three different signals. You've got a low frequency, which is a slow signal up and down, a slow sine wave, and that's the blue one. You've got a mid frequency, which is a green, and then you've got a yellow high frequency signal, which is on top of the whole thing. And so those three overlap, if you pull them back, become that single blue signal. And there's no limit to how many of these signals overlapping you can have, and there's no limit to the complexity that you can make with sinusoidal signals. So if you go to really highly accurate results with really complex differential equations and whatnot, you can get a signal, pretty much any signal that you want to create, but you might need many, many hundreds of different sine waves in order to do it, thousands of sine waves sometimes. So Fourier analysis is essentially the concept of adding these smaller signals, these individual sinusoidal, evenly spaced signals, to make something complex that is not evenly spaced and more interesting, like the blue signal. So what does a filter do? A filter attenuates sine waves of different frequencies differently. So it allows some of the frequencies to shine through and show through while blocking some others. So you can have high pass filters, which lets high frequency through. So if I put a high pass filter on that Fourier transform over there, I'm going to let only the yellow signal out, and the green and blue are just going to disappear. Essentially, I'm going to filter them out. Likewise, if I have a low pass signal, it's going to get rid of all that high frequency yellow and also probably a lot of the green in there too, and it's just going to let your blue show through. And then if I have a band pass says I'm taking some kind of band in between a high frequency and a low frequency, and a band pass filter will let me look at that mid frequency, so the green one. So these are all different strategies to let us look at individual signals that come out of it, out of a more complex thing. So in red here, if a true signal and noise signal are different frequency ranges, then a filter can separate them. So if your heart is beating every second and your noise signal is a totally different range, which it's every like 60 hertz, 60 times a second, it's pretty easy to separate those two out using a filter. The more different they are, if your heart is 1 second every second and the noise frequency that you have is 10,000 hertz or kilohertz or megahertz even, it becomes even easier to separate them out. And the filtration techniques work even better. So there's a lot of cool stuff you can do with sound in this, and I'd encourage you to try to test some of these out on your op amps. So your MyDAC is capable of outputting different frequencies. So output some frequencies, listen to them, from your op amp, and then try to clean up the signal. Put a low pass filter on there. So how does it sound? Put a high pass filter on there. How does it sound? And as a tip, you're going to hear totally different things if you tune your circuit right. If you put a low pass filter on, it's just going to be the bass of whatever you're playing. So whenever you have a subwoofer, the subwoofer is just letting your low frequencies through, because you don't want to put your high frequencies on the sub. It doesn't come out sounding very well. Likewise, you don't want low frequencies on like your tweeters. That sounds miserable too. And that's why, like, if you listen to music out of like normal computer speakers without a subwoofer, usually you don't get any bass in there. It sounds kind of tinny, kind of crappy. So that's why. So again, these are all things that you can experiment with on your own, just to kind of get the concepts into your head of why different frequencies are important and the filtering process used in order to amplify or to silence some of those frequencies. So here we have a little bit more of a breakdown of Fourier functions and Fourier analysis. And again, the overarching concept of this is any function of time can be constructed by adding sine and cosine functions, essentially sine functions of different amplitudes, frequencies, and phases. So by changing amplitudes, frequencies, and phases and adding more and more signals, and you can make very complex signals. And this is a really, really cool concept, and it's a very important concept, and I'm going to try to really harp on this because you can do so many cool things with this. Not just from sound, but you can also use this for image processing to remove patterns out of images. If you have noise, you can use this for MRIs if you have noise from like an LED or whatnot. So there's a whole bunch of different things that we can use to remove some of this noise, and that's the fundamental principle of that is the Fourier analysis, or Fourier transform and later analysis. But right now, Fourier analysis. So if we look in the top left chart, we have a fundamental frequency, and then we have a harmonic there. The red and the blue. If we add those red and blue together, essentially just take a value for them. So assign the very top of that red, the amplitude of the red one as 1, and assign the top of the amplitude of the blue as 0.5. And at every point, you're going to add them together. So right at the origin there, you're going to have 0 plus 0 equals 0. And then you're going to have, coming up a little bit, like 0.5 plus 0.5 equals 1. And then you're going to have, the blue line goes down, so it's actually going to start dipping out, sort of. So if we go over directly right of that, you're going to see when you add those two signals together what the resulting signal looks like. And you're going to actually start to get some interesting patterns. So this is almost kind of becoming a square wave. We have like 3 little dips, and then we have a really big dip going down to the bottom where it's negative, and that's the other side, the negative amplitude, the negative side of the amplitude, excuse me. And then you have 3 more dips, and then you're going to go back up to 0. So now let's look if we increase the frequency again. So we add another frequency in on top of that. We add the 5th harmonic in. And the 5th harmonic, again, it's the signal, it's essentially waves that align. So if you're playing violin, if any of you play violin, and you want to get your 3rd harmonic out, and the 3rd harmonic is a very high frequency pitch, you actually gently, ever so gently place your finger on your string, and by doing that, you're actually breaking the string up into a smaller location, and you're changing the vibration of it to make it extremely high. And so it's a neat little tip to be able to play very, very high notes. The problem with it is you have to be very quiet when you play them. You can't play usually your 3rd harmonic or your 5th harmonic very loud. They're quiet. However, I digress. So let's go into this. So anyway, we have our 5th harmonic plus our 3rd harmonic plus our fundamental frequency now because we're taking the output and we're adding another 5th harmonic. And if we look at that, we're going to get another even more square wave. So the more and more of these signals that we add on, the more and more harmonics, the more kind of square it's going to become. Eventually, you're going to be able to approximate a square close to infinity by doing it this way, which is exactly one of the ways that we can approach a square wave. So again, in the equation down below, this isn't that bad. It's essentially showing your fundamental frequency, and every single time you add a new frequency to it, you're just increasing your harmonic terms. So the 2nd, the 3rd, the 4th, the 5th, you're just increasing those terms and adding them together again. So that's building your more complex signal up. And so to tie this full circle again, the Fourier analysis allows us to add signals together to make more complex signals, or subtract signals to make simpler signals. And these signals are approximated to sine waves or cosine waves. And the way we can change them is and add them to get different variable signals is through changing their amplitude, frequencies, and phases. So this slide is a refresher in case you forget your physics 2 from E&M and wave theory. But essentially, here's a sinusoidal signal and the equation for sinusoidal signals. Especially, we're going to look at them in terms of voltage over time in this class because that's usually the most important. Like an alternating current signal the voltage is going to change as a function of time. That's just generally what we're looking at in electrical. So V of t equals Vm sine omega t, or if you want to do that and you want to break omega down, if that's more comfortable, you can get Vm sine 2 pi ft, where f is the frequency. And so to look and bring that back to the picture of what's happening in a wave, we've got our amplitude, which is essentially our height of from our zero axis to the top of our wave. We've got our period, which is how long it takes one wave to go all the way positive, all the way negative, and come back to zero. We've got our time shift, change in t, which is our phase, so how we align the waves up, back and forth. And we've got our peak-to-peak voltage, VPP. Our peak-to-peak is essentially our amplitude, usually in a sinusoidal one, our amplitude times 2, because it's going the whole way up and the whole way down. So that's the difference. It's related. Everything here is kind of related. So again, if you want to remember, if our normal sinusoidal wave is Vm sine omega t, which is the one that this is pointed to in the middle, you can shift that over by changing your constant there, essentially the phase of that, and you can have a time shift in order to do it. So this is a basic introduction to sinusoidal, basic review, I should say, of sinusoidal signals. If you find this even remotely difficult or you don't remember, I highly recommend going through YouTube, watching a couple videos. I can post a few. That way we can essentially crinkle out, iron out those wrinkles. Wow, I completely messed that phrase up. Iron out those wrinkles. And that way we can move forward faster, because this entire chapter is going to be about, and actually a lot of the future stuff is going to be about sinusoidal signals. A lot of filters are not as interesting in DC because DC don't really change. Filters, like all these signals, are changing up and down. Up and down is interesting, and that is what we need sinusoidals for. If it's just a flat line, like what is your peak to peak? What is, I mean, like it doesn't even, some of these terms don't even make sense. So anyway, let's continue on. So to get into RC and RL circuits, which are the easiest two, we're going to look again at resistors, capacitors, inductors, how to add them, and a little bit more background just as a refresher again in case you forgot it from the previous. Again, I encourage you, this is more of a refresher, not supposed to be the first time that you learn this material. So go back through your notes or, again, look through your book or some external sites to brush up. So again, we have resistors here. Resistors dissipate energy through heat. It resists the flow of current all the time. That's what it does. And they're generally the ones we work through are linear. So V equals IR, pretty simple. Inductors, which are L or measured in the units of henries. Inductors store energy in a magnetic field created by a current flowing through a coil. So this same field resists changes in current. So when you turn something on or off, or when inductors like powered and depowered, there's some of that energy is stored in the magnetic field and allows essentially some current to flow through after something's been unplugged or whatnot. Finally, we've got capacitors, the symbol for C, and their unit is farads. And capacitors are just two plates with some dielectric material between them. And capacitors store energy in charge, which is an electric field in between the plates. So that's essentially their way of working. And we're going to look at some of the equations and what this means for changing voltage, changing current, going through the next couple slides. So here are the equations for R, L, and C. R, again, is the one we've been most familiar with, so we're going to go through that first. If we want our equation for voltage with R as a function of current, V of t equals R I of t. So if you really want to simplify that down, V equals IR. And we've been using Ohm's law the entire way through this class. But this is a way of writing it out through time, because we've been using it at steady state, so a DC voltage where things never change, so time essentially doesn't really matter. It's always going to, a 9-volt battery is always going to be 9 volt until it gets drained or whatnot. But mathematically, a 9-volt battery is always 9 volt. And so we haven't really cared about time. But if you have a sinusoidal frequency that's going 0 to 9 and negative 9 to 0 again, 0 to 9 to 0 to negative 9 to 0 again, excuse me. Now suddenly time is going to matter with that. So underneath there, we've got, again, we've rearranged it to be, it's instead of V equals IR, it's I equals V over R. It's a simple mathematical algebraic rearrangement. So finally at the bottom, this is the new concept. We have Z of R, which is impedance. So impedance is a little more interesting than resistance. For a normal resistor, impedance is resistance. Essentially, a resistor and resistance is how the current is impeded going through that little resistor. So by definition, they're similar. However, when we get to more complex things that change and have different frequencies and essentially sinusoidal properties, impedance becomes much more complex than just R or just a solid value. It becomes actually an equation that we can calculate out. So that's going to be important coming up. For now, no, for resistor, impedance, and resistance are about the same. So in the middle here we have L, which is our inductor symbol. And our inductor is going to be, again, the voltage is going to equal L, or the inductance, with respect of I to di dt, so the change in current over the change in time. Again, it's storing some of it in its magnetic field, so when you unplug it, some of that current comes out. And again, that's based upon time, and that's the equation essentially, though, for seeing an inductor. So you can charge, I shouldn't say that. You can store a magnetic field in the inductor, and there's a function of time, so it's not immediate. You have to have time for it to fill that magnetic field, and you also have time for it to reduce from that magnetic field coming out, even if something's unplugged. So you can think of it as storing a little bit of storage in that regard. So down below, we have the current rating for an inductor. And the current I of t is much more interesting. It's 1 over L, so the inductance value, the 1 over L, so the inverse of the inductance. So as you get higher inductance, this drops. You get the integral from 0 to t of v of t dt plus your initial current, whatever that was, I of 0. If you plug something in, your I0 is 0 because you just started. If it was already plugged in, then your I0 is some value, and you can add that in. So inductors are kind of, if you're looking at this, inductors are our integral circuit. Our resistors are just essentially multiplying by a normal constant, so like a slope circuit. And we'll get to capacitors in a second. But if you look at our impedance for inductors down below, it's j omega L. So the inductance value, you have omega and you have j. So essentially, it's a function of the specific signal going through. So you kind of need, well, you do need a sinusoidal signal to make an inductor work. If you have a DC signal with an inductor, you're going to see, and I'm going to walk through this with you, it's kind of pointless. Like it's a short circuit. DC and inductors really don't do that much. You want some kind of frequency in order to make an inductor work. And then finally, on the right, we have capacitors. Our voltage equation for capacitor is 1 over c, the integral of I of t dt, and plus whatever the initial voltage is. Because again, a capacitor is storing charge. So there's a great lab that we're doing in Physics 2, which is essentially the time constant of charging a capacitor of an RC circuit, a resistor and capacitor circuit. And we can look at how to do that in this chapter and why it works at a more deep and interesting and actually beautiful mathematical level. So the equation for current through a capacitor is I of t equals c dv dt, so derivative of the voltage over time. So it's kind of, in some ways, the reverse of an inductor. And that's kind of interesting too, and we'll see how we can use this out in the future. So finally, we have the impedance of a capacitor, which is 1 over j omega c. Again, it's kind of the reverse of an inductor. So using these three pieces, we have an interesting thing where we can multiply something by a constant, which is r, or multiply just in general. We have the ability to take an integral of something, and we have the ability to take a derivative. So this allows us to solve differential equations now using these three pieces. And we're going to be able to do some really cool and fascinating stuff, especially if you couple this with our knowledge of op-amps and a simple frequency generator, to being able to solve very, very complex differential equations very quickly. So let's continue on with that next. So in this slide, we're going to look and we're going to bring things back to basics to tie everything together before we get into much more complex things. But here we're going to look at voltage dividers. So we did voltage dividers early on in the class, I think chapter 1 or 2. And essentially, we have two things with the voltage divider. Well, four things. We have our voltage in, we have our resistor 1, we have our resistor 2, and our V out. That's the way I look at it. So if we really want to run through the math on this, which I encourage you to go through, it's not hard. Voltage dividers are pretty simple. V out equals V in R2 over R1 plus R2. we can actually look and we can simplify this into a function of gain, which gain equals V out divided by V in by definition, which usually we're taking some percentage of the total V in voltage and we're giving some percentage of that voltage to the V out. What that percentage is depends entirely on the ratio of resistors that we've chosen. So in this specific case, if we plug through these values, again, you should do this so you have more familiarity with them. You're going to see our gain is 2/3, which means whatever our V in is at these particular resistor values, our V out is going to be 2/3 of our V in. Again, 2/3, like you can do that into a percentage as well, however you want to do this, to be able to understand that you have essentially a gain there. It's a gain of less than 1 because you're taking power out of the system with that first resistor, which makes sense conceptually. But this is a neat way of looking at voltage dividers. So we're going to continue on with why this is important. So now let's take that that voltage divider example, make it a little more complex to fit some of the new things that we're learning conceptually. So this is a little bit more of an esoteric example, but I think it's very useful as well. So instead of looking at these as resistances, let's look at them as impedances. And again, impedance is related to resistance, but it's a little more, it's more complex because you have a signal coming through. Previously, a resistor is just a linear line. It's V equals IR. Impedance has more to it than that because it's looking at the waveform. It's incorporating part of that waveform into your impedance. So instead of having an R, let's put Z's in for our two impedances. And instead of having two resistors, let's put in two inductors. And this is a way that we can look at gain based on impedances. So you can have gain, which is output over input, of Z2 equals Z1 over Z2. So if I have two inductors in there, it's going to be the value of the two inductors and the omega j. And if the omega j are the same, which they're going to be based on the source, you're going to have the value of the inductances change your impedance. So that's going to be creating your gain and your V out. Same with your capacitors. You can plug that equation in, one in the reciprocal with or 1 over j omega c, and that's going to give us our impedance versus the capacitor if you have two capacitors. So the cool part now is that you can mix and match these because the impedance is independent of resistance. So you can have an R and an L circuit, or you can have an R and a C circuit. And this is an interesting way of being able to look at gain based on a voltage divider circuit. So you don't need just resistors to make a voltage divider circuit. You can have capacitors to make a voltage divider, or a resistor and a capacitor to make a voltage divider. Now, there's a caveat to this as well, though. You got to look at your source, because for a lot of DC sources that we were looking at before, resistors will only work because if you have no omegas, let's just say you have a DC, which is a solid line, and there's no sinusoidal function, how are you going to get your j omega? You have no frequency. There is zero frequency, so that's going to cancel out. So you're going to get what? If that cancels out in the ZL, you're going to get 0 there. And in the ZC, you're going to get 1 over 0, which is impossible, but you're tending towards infinity, so that's not going to work either. And so infinite resistance for a capacitor versus 0 resistance for an inductor. 0 resistance for an inductor is just a short, and then infinite resistance for a capacitor is a gap in between. So again, that's just an interesting way of looking at it. So there are caveats to this, but this is a good way to explain impedance as a form of a voltage divider. So in these next slides, we're going to introduce transient responses, which are different than what we've done before. Previously, we've done steady-state responses. A DC battery has a steady output. A 9-volt battery outputs 9 volts. It doesn't really oscillate or anything. There's not really a sine wave coming out. However, transient responses are changing. Transient means change. Change. So changing responses. So this is responses that have essentially some type of sinusoidal signal or whatnot. So this works, these analogies work for both electrical or mechanical, whichever your mind works better with. So in like mechanical, like springs are oscillating up and down, up and down, up and down. That's a transient response. If I just push on a wall, nothing's happening. It's a steady state response. But if I push on a spring and it goes back and forth and oscillates, now I have a transient response. So right now we're going to look at what transient responses are, what they look like, how to calculate them out, and why they're important in electrical engineering. So in this slide, we're going to look at transient responses of a DC circuit because it's kind of the easiest way to bridge the gap between DC and AC. So that's what this goal is. So here we have a really simple circuit. We have a DC, direct voltage power supply there, V of T, and we're going to have a resistor, a switch, and some kind of black box circuit. Again, we don't really care what's happening in that circuit right now. It's a black box. But what we're going to do here is it says at t equals 0, the circuit's open, and then we're presuming at that we're going to close it. So if we draw that out to make a diagram of it, we're going to have a step function where at any time before 0, it's open circuit, so no current is flowing, so our voltage is 0. So that horizontal line stays, that blue line stays at 0, except when we hit at the time 0. And immediately at the time 0, when we push that switch, we're going to jump our voltage up going into the circuit, whatever our voltage supply is, V of t. So this is called a step function because essentially you're making a step, just like normal steps with it. And so the step function is the transient response in this case. The external pushing on the push button is causing the change, the transient, again, changing response. You're pushing on the circuit makes the change, and that's what happens. That's the output. This voltage changes from 0 all the way up to V0, whatever your voltage supply is, and that goes into your current. So now we're going to look, what if I of t equals I sine 2 pi 60t? So essentially it's saying, what if you've got a sinusoidal wave or whatnot? So I'm going to look at these two examples, A and B. So A, this is a DC transient response. The way I look at this one in A is all the way up to 0, I have that same circuit where the switch isn't being pushed, so there's no current flowing, so everything is off. As soon as I press that button, now maybe I have a charged capacitor in there or some other circuit, and immediately that's going to jump up and give out as much current as possible, but that's going to fade off because it's not recharging. It's essentially depleting itself. So once we get out to sufficient amount of time, then we're going to have almost no current coming out. So essentially that's, you can even think of that if you want to go really conceptually as like a battery dying. Early on, once you push that button, your battery is going to start using its power up, and it's going to just keep dying and dying and dying, and never comes back because there's nothing else giving power to it in the system. And that's how I look at the DC transient response, because again, a battery is a good example of DC. Now, if we look down at B, we've got combined response to AC excitation. So this is showing if you have a sine wave in there for the current. So you're going, again, but before 0, nothing happens. And then once we push that button, essentially your current is going to start depleting quickly. But what's going to happen here is you're going to have it bounce around. And you're going to see it's actually going to hit some kind of equilibrium where it's bouncing the same amount up and down every time. And that's called a steady state response. And that can be really useful once your response goes to steady state, because that means it's a stable response, which is something sometimes very important to look for. Sometimes it's not important. Like, you don't want a steady state response on an elevator because the elevator would never land at the floor. If you're going down from the top floor of the building and you're going down to the ground floor and it keeps bouncing from -1 to 0 to 1 to minus to 0 to -1, it keeps bouncing up and down, and it never stops or never slows down, that's really bad. You're never going to get off that elevator. So again, it depends on what you're looking for. There's no right or wrong answer for this, but mathematically it's an interesting thing where your transient response is the changing response. It's the response in my mind that kind of only happens one time, where the steady state response is something that can happen periodically, and that's why it's a different response. So there are many different types of non-periodic waveforms, and a lot of these become really important in controls engineering. But we introduced them here in electrical because it's again, electrical and controls are essentially connected. The same type of math used back and forth. So the one we looked at in the previous was a step function, where you have something that's off, you do something, and immediately it turns on, and there's no time gap between the two. It's either on or it's off, and that's it. We also, though, have ramp functions. Those are slightly related and different. So ramp functions, essentially have linearly changing uh, output. So again, like a ramp function, as you go from time, you're going to increase linearly voltage versus time. We've got square pulses, which are another type of functions similar to a step function, or it's actually two step functions, one that goes up immediately followed by one that goes, well, a step function that goes up with a period of time, and then the step function that goes down following it. So that period of time is what we use to calculate out our square pulse. And the square pulses are essentially what your 555 timer has been putting out. They put a whole bunch of square pulses out. And then finally, we have an exponential function here, which increases exponentially or decreases exponentially. All of these are non-periodic, which means they're non-repeating. They happen once, and that doesn't happen again and again. So they're not necessarily, well, they're definitely not sinusoidal, but they can allow us to build more complex circuits and more complex signals that come out of it. You'll see these pop up a lot in future slides. So here we have a non-periodic waveform, which is a step function. And essentially what this is saying is at any time less than 0, you're going to have one case, and then something's going to happen immediately at 0, and you're going to have a second case come out of it after that. So anything before 0 is separated from the things that come after 0 by whatever that changing thing is. And you're going to get a nice little equation out of it, a step equation. Essentially 0 for t is less than t, and v equals 0 for t is greater than t, which means if you look before your test point or after the time you throw the switch. So here we have a step function in action, again with a push button. So I have a voltage source there, and I throw the switch at t equals 3. And what we've got there is then after that, the switch, essentially the circuit is closed at time when t equals 3. So if we look at what's happening here, when I close that switch, originally you have an open circuit. And that open circuit means no current flows, so that's 0 all the way up to t equals 3. And then once we switch the switch, now it's at v equals 0, whatever your voltage is, because the power is going through. And you see we've shifted that signal over, we've shifted that step function over by waiting 3 more seconds. And we've shifted over 3 seconds. So that's a cool way of doing it, showing a time shift. So let's say we do, let's just say we do the reverse. If we're going to start with an open circuit and then close the circuit. So that's what's happening here if we undo the switch. We have from all the time up to 0, we're going to have the switch closed. And then all the way from 0 to 3, the switch is still closed, so power is still flowing. And then we're going to open the switch up. And opening it's going to make the circuit open, an open circuit, and that's going to be drive it back down to 0 as a function of voltage. Ramp functions are also pretty interesting functions. So ramps can go up or down. They're always linear. You can have a couple different ramps actually next to each other and approximate more curved functions. Generally, there's better ways to do it, but sometimes that's a useful little cheat. So ramp functions, again, it's like anytime you see a ramp or a constant slope or a linear slope, you can think v equals IR. You can think of y equals mx plus b. And essentially that's what we've got here. We've got a slope, and you can calculate your slope out of your rise to your run. And so anything in this case A, anything less than 1 second, negative 1 second, is going to be 0. And anything greater than negative 1, you're going to start doing your slope, r of t plus 1, because your slope is going up. It looks like 1 over 1. So essentially, where you start your time is how you shift it over left to the right, your time shift. Likewise, you can shift it all the way over to the right, and you can make it start from anything less than 2, nothing happens. And then once you're at 2, you're going to start your ramp function. And so your ramp function and your step function are related, and they're related by this equation here, the integral of the step. Because, I mean, think of it. Like, if you integrate, you're doing what? You're increasing. So if you integrate a straight line, you can make it into a diagonal line. And likewise, you can make a diagonal into a curve. As long as you keep integrating them, you're going to get more and more complex functions. So this is your function here, r of t, to turn one into another, to turn a ramp function essentially into a step function, or a step function to a ramp function. So on this side, we're going to look at example 5.1, which is investigating the real versus ideal step function. So if we look in the top left there, that's our ideal step function, where immediately whenever I push a button, immediately it shifts from 0 to whatever the voltage is, and there's absolutely no difference in time in between. However, there actually is a difference of time in between because things in the real world take time to be able to change. And so essentially what you're getting here is you actually have a ramp function with two outcomes. So you have, in between your steps, you actually have a ramp. And you have your steady state before your -2, and this is in the picture A. You have steady state before -2. You have a period of time where it's transient and changing. And then after 2, you have a steady state. You've reached it again. So that period of time and change in there becomes very important. And we're going to talk about slew and what that means. But essentially, you have a period of time in there that you're changing. And if we look over at the right drawing, what this is showing in B is that you can create that ramp function, that step ramp step function, by adding two time-shifted ramp functions. Because what's going to happen is from -5 to -2, they're both going to be 0. Cool. That's a normal ramp. We already have done that. And then from -2 to 2, you just have that top increasing ramp. So again, the easiest way to look at this is take each of those blue lines at each of the points and add them together. So at -5, it's 0 plus 0. So you put a point as you're adding, that's a 0. And your outcome when you add the two signals together. You look at -4, 0, 0, so at -4 it's 0. -3 it's 0, -2 it's 0. Now at -1, that upper one is increasing at a slope, so your output is going to be 3. If we keep going up to 0, your output is going to be 6. We're going to go all the way to your time equals 2 milliseconds. And now suddenly we want it to cap off. We want that to reach steady state again and just be a solid voltage. And we do that by adding in the exact opposite negative, the ramp function. So literally it's the same ramp function as before, but negative. And in this case, 3r, the top one is 3r t plus 2 milliseconds, and the bottom one is minus 3r t minus 2. So it's the opposite, and it cancels that out. It cancels that growth out so that you have essentially a 0 again. And that's how you can take those two blue signals and you can pull them all the way back to picture A and make that original red signal. And the math is corresponding there too. You have two different signals, V1 and V2, and you're going to add them together to be VT, which is your red signal, your output. And the math is shown on how to do that based upon the 2 points. So another interesting non-periodic waveform is a pulse. And a pulse is something that turns on for a little bit, for a set period of time, then turns off again. So if you go into using more complex electronics, you have things like servos, which take a pulse, and the speed of the pulse, or the pulse width modulation, they call it, PWM, changes the angle of that motor. So if you have a slow pulse width modulation, it can be 0 degrees for the motor. And if you have a fast pulse width modulation, you can have the motor move to 180 degrees. And any space in between there, you can control by the pulse width modulation, the width of that pulse, modulated to a set time period. So let's look at A. If I have circuit A, which is a power supply with a single pole double throw switch, and I all of a sudden switch it, what's going to happen? If I switch it on and off real fast for 1 second, you're going to create a pulse because you're going to have power going into your circuit, and then it's going to go back off again. And so that's going to generate the red pulse that you see underneath there. The red pulse that you see underneath there. And it's going to show you there your equivalent input pulse, which comes from the equations we looked at before, which is, again, the pulses are rectangular because it goes from 0, turns on for a brief period of time, and then turns off again, creating that rectangle. And so in the blue box down below, you see your piecewise function for that that essentially pulse form. And it's a pulse that comes on and off. So it's a step function that comes on, waits for a period of time, and then a step function down. So step up, wait, step down. And that's what the 0, 1, 0 are doing in the piecewise function. You have 0, so nothing, your step up, 1, and then your step down again is your second 0. So if we look at on the right-hand side, you can see how the pulse kind of moves through the system and what different pulses look like. So a normal pulse on the positive side, you have a pulse on the negative side, and we have a negative pulse going upside down, which is going into the negative voltage. So all of these are different ways of doing and sending pulses through. So if you look at your 555 timer that we've been using, essentially the 555 timer sends out a set of pulses, and it's pseudo-periodic because they happen again and again at the same period of time, but it's also not pseudo-periodic because if you set it up right and you have a resistor that changes, then that's going to be changing the pulses that come out, and that's another way to look at it too. But you could also have your 555 output a single pulse. That's also possible as well if you set the circuit up. So anyway, this is pulses. Essentially, you have three pieces to your piecewise function. How's that for a tongue twister? And again, we can do waveform synthesis. We can add and subtract signals together. So to get our red pulse up there, we can have two different waves. We can have two step functions that cancel out. Well, they don't cancel, then they do. So in picture C in the bottom left, we have two blue signals, two different step functions. One's a positive, one's a negative. All the way up into 2, if you add them together, they're 0, 0, 0, 0, 0, 0 at 2. The top one increases to 4. So 0 plus 4 is 4. At 3 seconds, 0 plus 4 is 4. At 4 seconds, 0. At 4 seconds, we add in a negative signal that cancels out the first one, and that pulls our pulse back down to 0. So now we've added two different signals together to get that waveform, that pulse, that rectangular pulse. And the mathematics, again, are shown below if you want to review through that. It's pretty easy in that regard. So now we can also go to something more complex, like a trapezoid, which is putting together a whole bunch of different things that we've talked about so far. So the trapezoid is essentially taking 0, 0, 0, and then we have a ramp function as it ramps up that first end of the trapezoid. And then we have some kind of holding function, so we have a negative ramp function that cancels out that first ramp function. And now we need another ramp function to have it go down, and then we need another ramp function to cancel the downward function. So if you look at the wishbone kind of thing underneath there, you can kind of work through it. 0, 0, 0, and then we have our increasing all the way to 5 volts, and then we have our steadies at holding at 5 volts, and that's been done by the second signal that points down and cancels it out. And now we got to bring that signal back down to 0, so we add a negative in there, and we pull it back down with that negative ramp. And then once we're back down at 4, we want to average that out back to 0, so we add a positive signal back in to cancel it all out. And again, if you've been following along the math on this, it's signal plus the output signal equals the first input plus the second input plus the third input plus the fourth input. And these signals are just slopes, so we can add them all up in order to get our piecewise function for this waveform. So the whole reason we're doing this is I'm trying to show you that you can build with very simple mathematical equations, linear equations, these more complex shapes. And I want to introduce it this way with straight linear things because it's easier for you to calculate, it's easier for you to get your head around before we start doing the exact same thing with different sine waves and overlapping sine waves together. So make sure you really understand this. I think this slide so far of the ones we've looked at is the most important right now for understanding what we're going to do with Fourier analysis. We also got another piece that I kind of skipped over before. You also have exponential functions, and these are also non-periodic because, again, they have no frequency. They don't return. They happen once. So you have in A, you have the role of the time constant, and changing the time constant essentially is going to change how your exponent looks. You have a longer time constant, then you're going to have a slower decay. You have a shorter time constant, you're going to have a faster decay. In B, we have the role of the time shift, and that kind of just shifts it over. But there's more to it. It's not just a perfect shift over. You also have some other things. In C, we've got, again, the role of a decreasing. So this is a decaying signal, so like a battery that's dying. And then in D, you have something that's like charging up or filling up. So you have more and more being produced. So that's maybe as your solar cells are turning on in the morning, they're producing more and more voltage slowly. And it's not a ramp because the way the sun is setting is not necessarily linear. So this is an interesting set too. It's not just linears that you can work with. You can have these nonlinear forms as well. They add just the same mathematically as the linear ones. So in conclusion for this section, these are the four different types of non-periodic waveforms we've introduced: the step function, the ramp function, the rectangle function, or pulse, and then the exponential. And by using these functions, you can start to create much, much more complex descriptions and more complex signals. And I want you to get these linear ones, these easy ones down before we go to sine functions. So try to make an equation out. Y equals mx plus b. That's an easy one. That's just going to be a ramp. But try something a little more complex and see if you can make it into a function based upon building up these different functions that are here. And again, it doesn't have to match perfectly. In electrical, sometimes our signal that we want doesn't perfectly match our signal that we need, but we compromise. And that way, that compromising lets us get kind of close to it without being so mathematically exact that we can't finish it, or there's thousands of waveforms adding up or whatnot. Sometimes these simple ones can do a really good job. So anyway, with that note, I'm going to end this section. We've still got a lot more in Chapter 5, but please review through it. I'm going to probably put out some homework problems sometime this week too, so complete those on time. And yeah, I hope this helps you in the upcoming weeks, especially as we study RCL circuits and some other interesting electrical phenomenon.